All right, honors calculus. We have to know that most of the functions that you and I know are already continuous by definition, and we get to use that. So we really only have to worry about investigating functions at those values where it seems like they may not be continuous. All right, so let's get our list of what will be continuous. If f and g are already continuous functions, then all of these will be continuous functions. F plus g of x, f minus g of x, a constant times the function f times g function, f divided by g function as long as g of a does not equal 0. All polynomials are continuous over the entire set of real numbers. Think about it. F of x equals 3, the constant linear function. Its domain is all real numbers, and it's continuous over all real numbers. Think about f of x equals x minus 2. That's a linear function. Its domain is all real numbers, and it's continuous over all real numbers. Think about f of x equals x squared. Its domain is all real numbers. It's continuous over real numbers. Think about f of x equals x cubed. Its domain is all real numbers. It's continuous over all real numbers. You get the point. This you can just take as true, as long as you can identify the function as a polynomial. Rational functions, quotients of polynomials, they're continuous not over all the real numbers, but on their domains. So you know, when you think about a rational function, it could have some discontinuities in there, right? It could have vertical asymptotes or infinite discontinuities. It could have holes. If that's the case, those are not part of the domain of the function anyway. So we can say these rational functions are continuous on their domains, which means everywhere except at the vertical asymptotes and at the holes. Sine and cosine functions, they're continuous over all real numbers, right? They just keep going like this. Tangent function is continuous not over all real numbers, but over its domain, because remember the tangent function is doing one of these deals, right? Periodically like this, and it's got these vertical asymptotes. So what we would say is tangent is continuous on this domain, that is everywhere except at the vertical asymptotes. See how domain is super important here. All right, how about exponential functions? Exponential growth, exponential decay, which is like this. Well, that's continuous on all real numbers. The domain is all real numbers, continuous on all real numbers. You never have to lift your pen to draw these functions. Root functions, like square roots of x, right? It's continuous, not over all real numbers, but over its domain. Because, I mean, what if I had f of x equals the square roots of x? What's the domain? X is greater than or equal to 0. Why? Because you can never have, you can never put a negative number into the square root function. There can never be a negative underneath the square root, or else you get an imaginary number, which is not really in our world. So you're going to get out values like 0 and greater than 0. You're going to get out values like f of x is greater than 0, if that makes sense. Yeah, all right. So remember, you can use these facts. Now, in your homework, the text may ask you to not use these facts. You know, early on, it may say, justify using limit laws or justify using these kind of laws. But the end goal is to realize we're going to be able to use these facts plus our limit definition of continuity to examine those kind of suspicious places. And you can see very clearly how important graphs are and domains are. Thank you. All right, honors calculus, let's link together functions, domains, continuity of the functions, and then let's take some limits of those functions. Let's see what I mean over here. What type of function is f? It's a rational function, right? How would you get the zeros? Take the zeros of the numerator. How would you get the vertical asymptotes? Take the zeros of the denominator. You could graph it. What you should notice immediately is there's going to be a vertical asymptote at x equals -3, and there'll be a hole. This is happening in the numerator and the denominator at x equals -1. So the domain is, and you should use this notation, the domain equals the set of all x that are elements of the real such that x doesn't equal -1 and -3. Now, you didn't even need to know much about a rational function other than you don't want to have a 0 in the denominator to be able to figure that out. How does domain relate to continuity? Remember, rational functions are continuous on their domains. So f is continuous on basically all real numbers except for -3 and -1. How do we write that in interval notation? You should use interval notation. F is continuous on -infinity to -3, not including -3. From -3 to -1, not including -1 and -3, -1. And from -1 to infinity, again, not including -1. All open intervals here. Okay, let's just take a couple limits here. What if I said take the limit as x approaches 2 of this function? Well, how do you do that for a rational function? We just plug in the value. So plug in 2, what do you get? You get 4, 3, 5 squared, and 3, which is 12 over 75, I believe. Look, even though this function is not continuous at x equals -1, we can still take its limit because it's just a whole, right? You can still take a limit from both directions of a whole. What's the limit as x approaches -1 of the function? Well, you plug in -1, you get out a quarter. However, at the vertical asymptote, we would expect the limit as x approaches -3 of f of x to not exist, and that's right. The limit as x approaches -3 of f of x does not exist. It turns out they're both going down, and it's a volcano, right? They're both going down to -infinity, so you could write -infinity. But remember, when you write -infinity here, what you're really saying is does not exist, and you're giving more information. Okay. Here's a square root function, shifted over to the right by 1. Okay, what's its domain? Well, square root function looks like this, shifted over, it's going to be what you expect it to be. Domain is the set of all x that are elements of the real such that x is greater than or equal to 1. 1 works, right? 1 minus 1 is 0 squared, so 0 is 0, no problem. Only problem is we get a negative underneath that radical sign. So what do we say? G is continuous on the interval from 1 to infinity. Notice it's a closed interval on the left-hand side because you're including 1. That's okay. But you can never include infinity, so it's open interval notation there. Let's just try this. If I try the limit as x approaches 2 randomly, okay, no problem. You stick in 2 there, you get 2 minus 1 is 1 squared, so 1 is 1. Okay. But if I tried to take the limit as x approaches 0, could I do that? No, because 0 isn't even in the domain. This function is not even there. It's like going into pure thin air. So this makes no sense. So of course this would be DNE. It's a nonsensical kind of question. Okay, finally we look at this function over here. H of x equals cosine of x plus 3e to the x plus 1 over x squared plus 1. Look, it is a cosine function whose domain is all real numbers, continuous over all real numbers, exponential growth function, domain all real numbers, continuous over all real numbers. Rational function will be continuous over its domain. Its domain is all real numbers. There's nothing that can make the denominator 0. Why? Because no matter what you put in, whatever value you put in for x, you get a positive number. So, hey, what's the domain? The domain is x's elements of the real, meaning all real numbers. That's the perfect set notation, by the way. Interval notation for continuity, let's use that. H is continuous on all real numbers. How do we express that? Open interval from -infinity to infinity. Finally, let's just take the limit as x approaches some value. Let's take the limit as x approaches pi. What do? Just stick it into the function. What's cosine of pi? -1. It's cosine of 3e to the x, 3 to the pi. Cosine of that is 1 over pi squared plus 1. Now you should be really comfortable leaving that as an answer. That is a numerical answer and much more accurate than whatever calculator is going to spit out. All right, folks, I hope you're seeing the connections here between domain and continuity and realizing when you can take a limit and when you can't. Thanks.
Hello, students. What do you call a function in a function? S'more says a composite function.
All right, folks, good to see you again. Listen, we need to talk about what happens if you have a composite function. Now, really, you've been handling this for a while, but there's kind of a law or a theorem about it, so we'll talk about that. Here it is. The limit as x approaches a of f of x equals f of the limit as x approaches a of g of x. In other words, you can either plug a right into the composite function, or you can think about it as plugging a into the inner function and then taking the outer function of that limit. Under 2 conditions that must hold. 1, this limit, the limit as x approaches a of g of x, must exist. It
Can't be D and E. And f, the outer function, must be continuous at this limit. So whatever limit comes out here, f actually needs to be continuous there. Okay, now the truth is most of your functions, your basic functions, are continuous at most places. And your limits exist on most of these functions in most places. So very often this will work, but not always. These conditions always have to hold. Now, let's look at this thing. If I told you f of g of x is a function, clearly it's a composite function. We like to write it this way, f of g of x. What's the inner function? G. What's the outer function? F. How do we think about this? X goes into the g function, out comes g of x. G of x goes in the f function, out comes f of g of x. You know this. All right, so in this case, I'm saying that f of g of x is the cube root of sine of x. What's the inner function? Sine of x. What's the outer function? The cube root function. So we could use this theorem. So let's say we took the limit as x approaches pi over 2 of f of g of x. In other words, we took the limit as x approaches pi over 2 of the cube root of sine x. We could do it outright. If we did this outright, we just stick pi over 2 into this function and we get, sine of pi over 2 cube rooted, and that's the cube root of 1, which is 1. No big deal. But if you wanted to think of it in terms of this theorem, which at a base level you should be, you could look at it this way. Instead of the limit as x approaches pi over 2 of f of g of x, use the theorem to say that's the same as, f of the limit as x approaches pi over 2 of g of x. Okay, assuming these two conditions hold, which they do. In which case, you're really getting f of, which is the cube root of, the limit as x approaches pi over 2 of g, where g is sine of x. So you could rewrite it this way. Okay, then you take the limit as x approaches pi over 2 of sine of x, you get sine of pi over 2. Don't forget the cube root on the outside. Cube root of 1, which is 1. All right, thank you. Remember, for most of composite functions, you're still doing the same thing. You're just taking and plugging this value that x is approaching into f of g of x. But if you want to think it on a deconstructed level, then you're really using this theorem right here to get to where you want to go. Thank you.
Guess what? There's more to know about composite functions. Stop squirming.
That's right, folks. A natural outgrowth of what we just talked about is this theorem. If g is continuous at a and f is continuous at g of a, then f of g of x, the composite function, is continuous at a. All right. So let's see how that might work. H of x equals sine of x squared. Composite function, inner function is x squared, outer function is sine of x. So we would say f of x is sine of x, g of x is x squared. Now if we were to follow this theorem, we would have to investigate the continuity of the inner function. Well, sine of x is continuous on all real numbers, right? Open interval from negative infinity to infinity, and likewise, x squared is continuous on the open interval from negative infinity to infinity. So, what conclusion can we draw by this theorem? F of g of x equals sine of x squared is continuous on all real numbers on the open interval from negative infinity to infinity. All right, finally, let's get a harder function here. H of x is equal to 1 over square roots of x squared plus 7 minus 4. It's kind of a rational function, kind of a quotient of polynomials, but the denominator isn't really a polynomial. It's got a square root function in it, which is a little bit different. If we were to take this approach of trying to deconstruct this composite function, it would have to decompose it into these 4 sub-functions. I don't know if you can see that. The outer function is 1 over x. The next function is really x minus 4. The function after that is the square roots of x, and the function after that is this quadratic x squared plus 7. I've listed them up here for you. Then you'd have to determine where they're continuous. So like, what's the domain of 1 over x? X is an element of the reals where x doesn't equal 0, so you're continuous wherever f doesn't equal 0. G of x is linear functions continuous everywhere on the open interval from negative infinity to infinity. This function, square roots of x, is, what's its domain? Where x is greater than or equal to 0. And j of x, where x squared, which equals x squared plus 7, well, that's continuous everywhere. It's a quadratic function. Then you'd have to go through the steps of thinking about continuity. The inner function is continuous at a, and then the next function out of that is continuous at g of that, and then the next level. Man, that just, to me, that's really a lot of work. So, unless they explicitly ask you to try to think through that, which is going to take work, this is how we really approach, this is how I would approach trying to determine continuity of this function right here, h of x. I would say, hey man, what's the domain of h of x? You must see from the last few videos that there's a direct connection between the domain of a function and its continuity, right? Not for all functions, but for most of our functions. So I would look over here and I'd say, wow, what is the domain of this function? Well, first you kind of assume it's all real numbers, and then you eliminate the problem areas. So what are the problem areas? Clearly, if the denominator of this function is equal to 0, that's a problem. 1 divided by 0 is undefined. So if the square roots of x squared plus 7 minus 4 equals 0, that's a problem. Likewise, there could be a problem if you get a negative number underneath a radical, correct? So if x squared minus 7 is negative, or x squared plus 7 is less than 0, that's what negative means. If x squared plus 7 is less than 0, that's a problem. Well, when will the square roots of x squared plus 7 minus 4 equal 0? Well, if you solve this thing, when x is equal to negative 3 or 3. Can you see that? Negative 3 squared is 9. 9 plus 7 is 16. Square root of 16 is 4. 4 minus 4 is 0. Same if I plugged in 3. So clearly these are problem numbers, problem values for the domain. Likewise, x squared plus 7 is less than 0. When will this be negative? Well, never, because no matter what value you put in for x, what are you going to get out? A positive number. A positive number plus 7 is a positive number. So there's really no value of x that'll be a problem area here. These are the only problem areas. These only numbers are not in the domain. Well, this function is going to be continuous. It's effectively on its domain. So we'd say h is continuous on the open interval from negative infinity to negative 3, from open interval from negative 3 to 3, and the open interval from 3 to positive infinity. I hope you can see that just kind of thinking about the domains of functions, it's probably of the actual function is going to be easier than decomposing it all into all its subparts and thinking through the steps of this theorem. Nevertheless, be aware of it, and make sure you know when a function is continuous, and make sure you understand domains. Thank you. All right, honors calculus. One more theorem in 1.8. This is called the intermediate value theorem. It's quite important. It's not exactly intuitive until you think it through, and then you're like, oh, this is a no-brainer. Yeah, you definitely want to have it in your mind and store it in the back of your mind. Intermediate value theorem. Technically, if f is continuous on the closed interval a to b, and n is a number between f of b and f of a, then there exists a number x equals c in the open interval a to b such that f of c equals n. I remember when I first read that, when I was your age, I was like, what? Okay, so I'll make it sound very easy. Here you go. Let's deconstruct it. If f is continuous on the closed interval a to b, well, here's a closed interval a to b. I'm calling it 0 to 7. And here's a continuous function f, never taking my hand off the whiteboard. Closed interval, closed endpoints. If f is continuous on a closed interval a to b, and n is a number between f of b and f of a. Well, what's f of b and f of a? That's easy. Stick a into the f function, out comes f of a. Stick b into the f function, out comes f of b. I'm telling you what they are here. They're 5 and 1. I just made those numbers up. But it says n is a number between f of b and f of a. So we have to choose a number between 1 and 5. Let's choose we'll choose the number 3. That's definitely between 1 and 5. And this number right here is what we're calling n. Then there exists a number x equals c, so we're talking about an x value, c, in the open interval from a to b, such that f of c, meaning if we stuck c into the f function, it would equal n. So we kind of work our way backwards from n to here, and this has got to be c. I don't know what that is. Maybe that's like 5.5. Just randomly making that up. That's not so important. The point is, if you stick this number c into the f function, out will come f of c, and f of c is n, this number between f of a and f of b. It's just guaranteed by this intermediate value theorem. If you've got a continuous function, and you've got a closed interval from A to B, which produces a closed range, f of B to f of A, if you have a value between f of B and f of A, there will be a corresponding independent value between A and B. That's the intermediate value theorem. It doesn't actually sound very profound at all when you think about it that way, but that's what this is saying. Here's one of its uses. Your graphing calculator. It doesn't get zeros of functions the way you and I get zeros. How do we get zeros of quadratic functions, say? We use the quadratic formula, we complete the square, we factor, or we use our graphing calculator. The graphing calculator doesn't use any of those methods. It uses kind of an iterative method of trial and error to get itself down to where it needs to be. What it really uses is this concept of the intermediate value theorem, and here you go. Here's going to be a closed interval, A to B, continuous function f. A goes in the f function, gets f of A. B goes in the function, gets f of B. What's this theorem tell me? This theorem tells me that there's going to be some value here between -2, and 1, which is, let's say, 0. And that's going to be my n. That's going to be my f of c, such that there's an independent value c right here. I mean, I just randomly chose n to equal 0, but if I do, out will come this c, because f of c will now be 0. F of c is n, it's 0. Now, here's what's important. Look at this thing. That's a 0. That's a root. That's a 0 of this function. Notice, because a, or f of a, namely, was a positive number, and f of b here is a negative number, then because the function is continuous by the intermediate value theorem, I'm guaranteed to go through a x-axis. I'm guaranteed to have a 0. So what's the calculator doing? The calculator can kind of calculate this value, which is f of 1, and this value, which is f of 3, and get it out to be 1 and -2. And that's almost the value 0, isn't it? Well, it'll slowly hone in on this value 0 using iterative process, and it'll get you the exact 0. I don't know what the exact 0 is. Looks like it's probably something like the value 2. All right, intermediate value theorem in this case is going to guarantee there's a 0. And your calculator uses an iterative process to find it. All right, let me summarize 1.8 for you. Lots of stuff in there, but basic idea is continuity at an independent value, continuity at a point. You have to understand that definition. You also have to know that functions, the ones you know, are almost continuous everywhere on their domains. Most of them, not all of them. And wherever you think a function might be discontinuous, like probably where part of the function is not in the domain, or where you know about a jump discontinuity, you know about an infinite discontinuity, whatever, you need to be able to kind of identify that, show it graphically, also be able to prove that there's a discontinuity there using that notion, that algebraic notion, that law for what it is to be continuous. All right. Have a good one.